Okay, so we just finished looking at the different types of radioactive decay and what that looks like in a formula. So now we're going to add a little bit of math to it. And it's a little bit, it's not that hard. You can do this. All right, so the math is half-life. So a half-life is the time required for 1/2 of the whole entire amount of isotope to decay. What we'll notice is that different nuclei undergo radioactive decay at different rates, which I'll tell you about in a little bit. Each radionuclide has a characteristic half-life which is unaffected by external temperature or pressure. Kind of think of it's intrinsic. It happens inside the atom. It's part of it. It's for lack of a better term, DNA. So that's what it's made of. It has it. This is what it will do. Doesn't matter what's going on around it. It could like be burning. It doesn't matter. It will still stick to its pace when it comes to decaying. Radioactive atoms cannot be rendered harmless by chemical reaction or by any other practical treatment. Like I just said, like you could have put it in a fire and it's not going to do anything because that's not part of its makeup. It's intrinsic. It's inside. So at the moment, we don't have anything that can speed up the process. All right, so let's look at this math a little bit. It's not as bad as you would think. All right, so carbon-11 is used in medical imaging and has a half-life of 20.4 minutes. Carbon-11 nuclides are formed and then incorporated into a desired compound. That's the stuff they're going to stick them with. And they're injected into the patient so that they can get the images, basically illuminating whatever it is they wanted to see. And the entire process takes 5 half-lives. What percentage or fraction of a mass of 20 mg sample of original carbon remains at this time? So I know it's 5 half-lives. So here's the deal with half-lives. Half-lives are arrows. So anytime you see an arrow in this right here, an arrow means half-life. All right, so we're going to start looking at percentage. So you always start with 100% unless it says otherwise. Start at 100%. I got to put 5 arrows down. So what I would do is I would put my 100 right there, right? And then I'm going to put 5 arrows. 1, 2, 3, 4, 5. And then I'm just going to take a half of everything. That's a half-life. So 100, half of that is 50. Half of that is 25. Half of that is 12.5. And I ran out of room. This is going to be 6.25. And then this is going to be, oh, hold on. And then after that is a 3.125. And this is going to be percent. But here's the deal. Say if you start with a 100-gram sample, it's going to be grams instead of percent. Really nice and easy, right? So there is 3.125% of the carbon-11 left, the original carbon-11, right? Okay, so let's look at a fraction. So again, you do the 5 lines, 1, 2, 3, 4, 5. Okay, right like that. I got my 5 lines. I'm going to start with 1 because you start with a 1. Here's the deal. Put a 1 on top of everything. Okay? Make your life easier. Right? Go like that. And then, because it's a half-life, you're taking half of something. What you're going to do on the bottom is anytime you see an arrow, multiply it by 2. So 2, 4, 8. Sorry, my brain went wrong. 8 and 2 is 16. 16 and 2 is 32. So I will be left with 1/32 fraction of that carbon-11. Let's see if I'm right. Yep, see, right there. Okay, the last one is the mass. So we start with a 20 milligram sample. I'm going to erase what I have. And we're going to do the 5 lines again. 1, 2, 3, 4, 5. I've spaced it out a little bit more. So I'm going to start with the 20 milligram sample, and I'm going to keep milligrams across, just knowing that it's all milligrams. I'm going to end with milligrams in the end, right there. Okay, so half of 20 is 10.0 mg. Then it's a 5.00 mg. And then half of that is, oh gosh, 2.50 mg. Yeah, that's 2.50 mg. And then half of that is 1.25 mg. And half of that is 0.6, oh gosh, 625, yeah. There you go. See? And sometimes I know this because I've done this quite a bit. I've had to do this for other classes, so I'm pretty good at cutting things down. If you need to use a calculator, you are more than welcome to use a calculator. So we saw that the mass is 0.625 milligrams left of carbon 11. It's 1/32nd the original, and it is 3.125% of the original. Okay, well, let's look at an exercise in the yellow pages. So this one says, how many half-lives, how many arrows are required for a 100-gram sample of a radioisotope to decay to 6.25? Okay, so here's what we're going to do. We're going to start with 100 grams. So I'm going to put mass up here, just so you know that it is grams throughout, and I'm just going to write the numbers down. So I'm going to start at 100, and I'm going to put an arrow. Half of 100 is 50. I got to get to 6.25. All right, half of that is 25. Half of 25 is 12.5. Half of 12.5 is 6.25. Ooh, I've reached where I needed to get. All right, so how many half-lives is that? I just got to count up how many arrows. I've got 1, 2, 3, 4 arrows. So that was 4 half-lives. 1, 2, 3, 4. 4 half-lives have passed. All right, let's go a little bit farther. Half-life of mercury-195 is 31 hours. If you start with an 80-gram sample, how much of it will be decayed after, or undecayed after 93 hours? Okie dokie. So let's do this. First things first, I got to find out how many half-lives. How do I figure that out? Well, they tell you 31 hours is 1 half-life. What I'm going to do is 93 divided by 31. And I'm going to use my calculator because I can't do it off the top of my head. 31. I get 3. So I'm going to have 3 half-lives. 1, 2, 3. I'm going to start with 80. 80.0 grams. Half of that is 40.0 grams. Half of that is 20.0 grams. Half of that is 10.0 grams. There should be 10.0 grams of undecayed left. See? That is how I figure it out. Let's see the next one. So a sample of iodine, 126, with the original mass of 15.000 milligrams, loses 13.125 milligrams of the original mass of the isotope in 39 days. What is the half-life of 126? Okay, so let's see. What are we doing first? So the final mass. Let's figure out the final mass. It loses this much. So 15.000 minus 13.125 gives me 1.875 milligrams. I'm left with that. I start at 15. I end with this. So what are we going to do? I'm going to start with 15. 15.000. And I'm going to make sure I label this mg so I don't have to keep writing it down. So half of 15. And I'm going to get my calculator because I'm not that great with it, is 7.500. And I'm going to do another one. So I got to divide that in half. Gives me 3.750. And then I'm going to divide it again. Anytime I divide by 2, I'm putting an arrow. So I'm dividing that by 2. Gives me 1.875. Ding, 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 ding. That is where I wanted to go. So how many half-lives was that? That was 3. I've got 1, 2, 3 half-lives. Well, why is that important? We know that it took 39 days. So 39 divided by 3 means each half-life took 13 days. Because all I have to do is divide. It takes 13 days to decay. Let's see if my math is right. So 1, 2, 3. 3 lives into 395 days ends with 13 days for each half-life. Okay? So here's a really nice thing. We've already seen table N because table N will give you decay mode. Not only does it give you decay mode, but it gives you the half-life, how long each half-life is. And if you look down at the bottom, MS is milliseconds, S is seconds, MIN is minutes, H is hours, D is days, and yes, we have Y is years. Okay? All right, so let's look at another exercise. Almost last thing we're doing. Okay, so what fraction of a sample of strontium-90 remains unchanged after 56.2 days? So I'm going to look on table N. I'm going to find strontium 90. And strontium-90, SR90, and I'm going to show you what it looks like. Right there, SR90, according to table N, because I'm looking at my table N right here. My table N says that it is 29.1 years, right? That's how long it takes to decay one time. So if I have 56.2 years, all I'm going to do is divide 56.2 divide by 29.1, and it gives me roughly about 2 years, if you see. Oh, that one is a little bit different than mine. I apologize. So like I said, it's roughly about 2 according to this. I do have a little bit of different discrepancies in my slides as opposed to what's on here. Okay. So, in fractional value, if there's 2 half-lives, it should look like a 1/4. So there's 1, 2. Remember, the arrows equal that. So 1 over 2, 1 over 4. Okay, so a quarter of it remains unchanged. All right. Let's see the next one. A sample of phosphorus 32. A sample of phosphorus 32 decays for 57.2 days. If 8 grams remains undecayed, what was the mass of the original sample? So we're going to have to work backwards. Okay, so the last one is phosphorus 32. Phosphorus 32, P32 has 14.28 days. 14.28 days. And it says it took 57.2 days to get 8 grams. So I'm going to divide again. 57.2 divided by 14.28 gives me roughly four decays. So I'm going to put 4 arrows. And after my last arrow, that's where I'm going to do 8. And again, remember, I'm doing in grams. So it's 8.0 grams. So I'm just going to multiply that by 2, 16. 16 by 2 is 32. 32 times 2 is 64. 64 times 2 is 128. Should be 128 grams. So all I did was 7.2 days, divide by the 14.28, which you find on table N. And I found there's 4 half-lives. I put 4 arrows. I started at the reverse with 8, and I times my way back. Okay, let's see if I'm correct. Half-life, there are 4 half-lives. Working backwards, just like I showed you. Original sample was that. All right, so that is it for right now. And if you have any questions, let me know. Hope you have a great day.